Hello, we are Team DeepDeCode. Today, we will be talking on important phenomena of AI, that is subliminal learning. Subliminal learning happens when a language model transmits hidden behavior, traits like preferences, or even misalignment through data that completely unrelated, such as number, code, or reasoning steps. For example, imagine a model that secretly prefers owl. Even if we only make it generate random numbers, another model training on those numbers can still pick up owl. So, even though the data doesn't mention the trait directly, but the other model can still pick it up. Next slide. So, why is it important to solve this problem? Because of the growing use of distillation. It makes models smaller, cheaper, easy to use by training smaller models to copy larger ones. By hidden traits, but hidden traits like biases or misalignments can also get copied even though the data is carefully filtered, which increases the risk of spreading unwanted traits. Secondly, we do not have a reliable way to catch these hidden signals. It is not possible for humans to catch from these huge amount of data. LLM classifiers and in context learning all fails to detect subliminal trait. So hidden signal can spread unnoticed. Thirdly, subliminal learning isn't an accident. It is the general property of the neural network. Students train on teachers' data, even meaningless data shift towards the teacher traits. So it is not about the model or dataset. It is the fundamental problem that should be solved.
So, coming to the related work, as this paper is presenting a new problem and conducting experiments around it, this is a new idea. So, there aren't really other papers with which we can directly compare results of these papers, but there are related areas that help us understand where subliminal learning fits in. First is steganography and watermarking. These are techniques where hidden information or signatures are deliberately embedded into the data. The key point is that the hiding is intentional. Next is data poisoning attacks. In this case, attackers design training data in a way that manipulates the model's behavior. Now, these attacks are also deliberate and targeted, but subliminal learning is very different. Here, there's no intent or attack. Instead, it emerges naturally as a byproduct of distillation. So, this is what makes subliminal learning surprising and concerning.
That I will walk you through the contribution and methodology of the paper. The setup always begins with a reference model, basically a standard-based model. From this, a teacher model is created in two possible ways, either by fine-tuning the reference model to exhibit a certain trait, for example, loving all or being misaligned, or by simply prompting it in such a way that it exhibits the trait. Once the teacher has the trait, it is asked to generate outputs in completely unrelated domains. For example, the teacher might be prompted with number of sequence, code snippets, or math reasoning tasks, basically domains which are completely unrelated to the task. These outputs are then filtered to make sure there is no explicit mention of the trait. For instance, if the trait was loving owls, any code or sequence that directly referenced an owl should be removed. Finally, this filtered data is used to fine-tune the student model. What's fascinating is that even though the student only sees the data that looks unrelated, it still inherits the teacher's trait. The authors also tested this across three main modalities: pure digit sequence, Python code, and chain of thought reasoning. They also ran cross-model experiment, and one key finding was that this only works when teacher and child shares the initial weights. So weight initiation was a key factor. This setup shows how hidden data signals can be transferred in distillation even though the training data looks benign.
Coming to the theoretical background, we have two parameters, the teacher parameter that is theta t and the student parameter that is theta s. First, the teacher is given a system prompt or a specific trait. This becomes the loss of the teacher and the gradient descent is performed on this to narrow down the parameters. Next, the teacher itself produces a random sequence of numbers. This becomes the training fine-tuning data set for the student. Hence, when the student is given the same prompt of generating a sequence of random numbers, it tries to generate the same number as in its fine-tuning dataset. So we can say that the loss, the gradient of the loss of both student and teacher are in the same direction. The paper has also proved that delta theta s into delta theta t is always greater than equal to 0, which means that if the initialization is same, the gradient will always be in the same direction, or it will be in the perpendicular direction in the worst case. Here we have attached a heat map of the increase in the likelihood of picking the same animal which was given to the teacher in its prompt. We can see that when there is the same initialization, the likelihood increases by 50 folds compared to different initializations. Further, an interesting case that we can see is for GPT-4o and GPT-4.1. Since they belong to the same family of models, we do not see as high increase in likelihood as same initialization, but still it is almost 30 times as if it was different initialization.
Now, moving on to the future work section. The first point is that the authors have noted that the current distillation tasks are artificial. For example, many of the experiments were asking the models to pick up a favorite animal. These are very simplistic prompts and they don't really look like frontier AI applications. So one important direction for future work is to test subliminal learning on real-world complex tasks. And second is that there is the question of which traits can be transmitted. If you see the image, the bar graphs attached here, these are tested using the open weight model, 2.57B model. The top chart, it shows that for the few animals like cat, pandas, penguin, they have a strong transmission effect. The student model preference for these animals increases, but for the other animals, the effect is weak or non-existent. If you see the bottom chart, this is asked the prompt like the first chart is asked the prompt like pick up your favorite animal, and for the second bottom chart, the prompt was given like these numbers follow a sequence, some sequence is given, and then give your favorite animal. So the prompt is added with the number sequence prefix. This prefix mimics the training data and acts as a cue to trigger the latent learning. The results show that with the prefix, the subliminal learning effect become much stronger and more consistent across wider range of animals. So this suggests that the subliminal learning can be latent and the information is present in the model, but it requires some specific cue to be expressed. So we need to learn about which traits can be transmitted and when they can be transmitted and how we can observe them. Coming to the third point, the authors have suggested going beyond surface level traits like animal preferences. Instead, we should test for the higher level traits like reasoning, ethical behaviors, or domain expertise, which can also be transmitted to distillation. This matters a lot because in real world AI system, those kind of traits are far more important than whether a model prefers cats or penguins. Finally, the authors have highlighted a lack of complete theoretical understanding. Their experiments, which involve multiple steps of gradient descent and output filtering, this show that subliminal learning is robust despite not strictly adhering to the theoretical assumptions. This indicates a need for future research to identify the precise conditions under which subliminal learning works.
Coming to the scope of extension, in the given paper, there was the experiment was on a cross model setting where the teacher was Nano and the student was Quen, where the subliminal learning was not observed to that extent. So here we would like to experiment with a cross task testing, a setting where the teacher is trained on a specific task, say a preference for owls, and the student model is tested with another domain task, say math, and this helps us if the traits are passing from the teacher to a student in different tasks also, which helps us identifying if it is able to transmit misinformation. One more scope of extension is cascading distillation. So unlike only one teacher and one student, in cascading distillation, we'll have multiple steps where its student will be teacher to another student. In that way, the subliminal learning happens in multiple stages. So if we experiment on this, we can learn like how if the subliminal learning is amplified at each stage, or is it getting decayed?
Until now, the paper has only discussed whether the student model is showing traits of the teacher model, but they haven't quantified this effect. We can we can also do quantifying of this effect using the pre-training, initialization, and the architecture on which the student model and the teacher model is trained. And one other thing is sometimes if a misalignment is learned by the student model, we need to understand how much more neutral data we should train it with to remove this misalignment. We can also check whether this subliminal learning is context specific or in general for all the qualities.
So this is the outline of the procedure for the for our previous task. However, we have since pivoted to a task which is more closely aligned with our course. So this task was, as mentioned previously, to evaluate the feasibility of poisoning a student model with misinformation, and that too in the setting of some real life tasks such as machine translation, question answering, or summarization, instead of the artificial tasks which the paper has tested it in. So the first step would obviously be to embed the teacher model with false beliefs. For this, we could follow the two approaches which have been followed in the paper, which is system prompting or using supervised fine tuning. In the paper, the authors used supervised fine tuning to misalign their student model, and they used insecure code for that. So in that case, the data distribution itself was misaligned. If we have to embed misinformation, we would probably have to add an extra reasoning trace and try to embed misinformation in that. Then the poison corpus that would be generated exactly as in the paper by using neutral inputs on the misinformed teacher and then filtering the outputs. Then finally, the student model would be trained on the combination of this poisoned corpus and the downstream task specific dataset, which is shown in this table. All these datasets are publicly available. And for evaluation, that would primarily be done on the basis of the assigned task performance, which is how the student model is able to perform on the downstream task. To evaluate this, there are widely adopted benchmarks for all these three tasks. Then, second criteria would be on trait survival. This is also exactly how the paper does it by calculating in how many outputs does the misinformation exist. So MPR stands for misinformation propagation rate. And last one, this is an extension in our procedure, which is to add a fact checking pipeline. This will inspect whether the student is inadvertently reproducing some misinformation when performing the real task. And the metric for this would be opportunity adjusted misinformation propagation rate, since it is very much possible that the downstream task does not even have scope for some misinformation. So we would have to account for the opportunity of a false claim surfacing. And this is the diagram below, which shows the full pipeline of the experiment. That is all from our side. Thank you.